Welcome, everyone. I'm Bill Sanders, the W. William D. and Nancy W. Strecker, Dean of the College of Engineering. Welcome to this College of Engineering's webinar series, Faculty Insights, a 20-minute briefing. Thanks for being here today. In this series, faculty from across the College of Engineering share insights about their research, its impact, and a perspective on the future. Following each 20-minute presentation, attendees will have an opportunity to direct comments and questions to the speaker. Our speaker today, David Rounce, Assistant Professor of Civil and Environmental Engineering, will give a presentation entitled From Peaks to Coast, Leveraging Glacier Projections to Increase Resilience of High Mountain and Coastal Communities. During this program, he will discuss the latest of glacier projections and show how they're being used to support mitigation and adaptation efforts to help communities become more climate resilient. David joined the Civil and Environmental Engineering Department here at CMU in the fall of 2020. He received his bachelor's in civil engineering from Villanova University, his master's in environmental water resources engineering, and his PhD in civil engineering from the University of Texas at Austin. David conducted postdoctoral research in the glaciers group at the University of Alaska, Fairbanks. David's research seeks to quantify the response of glaciers, water resources, and hazards to climate change to inform adaptation and mitigation efforts at the local, regional, and global scales. His work uses computational models informed by remote sensing and grounded in field work to produce actionable information. Before I turn over the screen to David, I'd like to remind you that to please use the question and answer feature at the bottom of your screen to submit your questions to David regarding his presentation. You can do this at any point during the presentation, and we'll get to the questions after he finishes. Mara Kudrick, Executive Director of Major Gifts for the College of Engineering, will be moderating the question and answer session with David at the conclusion of this presentation. David, thanks for being here today. I'm really looking forward to your talk. Now over to you.
Great. Thanks for having me here, Dean Sanders, and thanks for the introduction. It's really a pleasure to be here and share a little bit about a topic I'm incredibly passionate about, which is really how we can leverage glacier projections to increase the resilience of mountain communities and coastal communities all around the world. So let's dive right in. So glaciers are truly sentinels of climate change. They directly respond to changes in temperature and precipitation, and watching them evolve over time really makes this crystal clear. So here's a depiction of Rhone Glacier in Switzerland in 1850 compared to 2000. You can see that the glacier has thinned considerably as well as retreated considerably. The same thing is happening in glaciers all around the world. So here's an example of a tidewater glacier in Alaska, John Muir Glacier. That means a glacier that terminates into the ocean. You can see it here in the 1940s, here again in the 2000s. The glacier has thinned substantially and retreated such that you see a lot more water instead of ice. Here's a glacier in the Everest region of Nepal. This is where I actually did my PhD research, not in 1955. But you can see it in 1955, and here's the example in 2007. Once again, you see that the glacier has thinned substantially, and as it's retreated, it's actually formed a large proglacial lake that is now considered to be a flood hazard for downstream communities. And that's one of the things that I was looking at in my PhD research. So today, I'm going to be talking about glaciers. Specifically, I'm going to be talking about mountain glaciers. And these mountain glaciers, they represent 1% of the total ice on our planet. So most of the ice is actually in the Antarctic ice sheet. A lot of it is also in the Greenland ice sheet. And then this tiny sliver is those mountain glaciers. And you might ask yourself, why am I focusing on this tiny little 1% of ice? Remarkably, this 1% actually contributes 20% of the increase in global mean sea level. And it's projected to continue to be a leading contributor in sea level rise moving forward over the course of the next century, which I'll show you today. So we care a lot about sea level rise because the glaciers are a primary contributor. there's also more than 630 million people that live within 10 meters above the sea level. So hence, whatever happens to the glaciers is really critical for all coastal communities. Beyond sea level rise, the glaciers are also a really important water resource. There's roughly 2 billion people that live in or directly downstream from glaciers, and they could be negatively impacted by the changes in water resources. Climate, this is something where as the glaciers retreat, they expose darker land. This is why you get the Arctic amplification, which is where the Arctic is warming 4 times faster than the global mean. This is really driven more by the ice sheets and by sea ice changes, but the glaciers do have an impact here too. Ecosystems and culture, it's probably no surprise with the pictures of glaciers you've already seen that people really want to go and see these in person. There's roughly 3 million people per year that visit Alaska's glaciers and national parks each year. And then you've got Iceland, Europe, New Zealand, Patagonia, really all over the world. So they really draw a lot of people. They also provide really important ecosystem services. They control water temperature, they control water flows. Icebergs from calving glaciers can actually be very good habitats for raising seal pups, for example. So lots of services there. What I studied for my PhD was glacier outburst floods. A recent study estimated that roughly 15 million people are exposed to glacier outburst floods, primarily in developing countries. But we do have these in developed countries as well. If anybody's seen the news in Juneau, every year since 2011, they've had an ice dam glacier outburst flood. And the last 2 years have been really severe. We actually just got word that we're going to have a project funded to work on that problem moving forward for the next 4 years. And then the last one I'll talk about is glacier instabilities. This is where you have rock falls, avalanches, landslides. You also actually have hanging glaciers that detach and can be really hazardous as well. Now, my research, it primarily focuses on these 4, and I'm going to really focus just on sea level rise, water resources, and a tiny bit on that culture and ecosystems at the end. So our goal is really to quantify how are these glaciers responding to climate change. And we do that, we built a state-of-the-art global glacier evolution model over the last 7 years, and we can continue to improve it to this day. And we use this model to simulate how all 216,000 glaciers around the world are going to respond to various climate change scenarios. Now, before we take a look into the future, it's important to understand the past. So in this regard, one of the most exciting developments that's happened since I've gotten my PhD is really the proliferation of satellite images, as well as the advanced analytical techniques that we can use in order to use that data to monitor how the glaciers are changing. So we now have measurements of every single glacier, all 216,000 glaciers, and how they've changed, for example, from 2000 to 2019, which is shown here. So you can see this mean elevation change rate. Red colors are showing really highly negative values where the glaciers thin by at least 1 meter per year. The yellows or the blues are showing where you have really no elevation change or actually some slight gain. We see this slight gain in the Karakoram region in the center of high mountain Asia. It's referred to as the Karakoram anomaly. I'm happy to talk about it later. But what's really clear is that we have this very detailed spatial distribution. What's happening in some regions is different in other regions, and we can now use this data in order to calibrate and validate our models. And so we use this data to calibrate them, and with our calibrated model, we can then start to look into the future. So we run our model for an ensemble of general circulation models, and we look at different emission scenarios. And these emission scenarios are referred to as shared socioeconomic pathways, or SSPs. And we also run them for these older RCPs, or representative concentration pathways, so that we can see how the advances in our new simulations compare to some of the older work. So the solid line is showing you those different shared socioeconomic pathways, where that 1-2.6 is really a low emission scenario where you're getting around 2 degrees of an increase in global mean temperature by the end of the century relative to pre-industrial levels. The SSP 585 is really exceeding about 4.5, 5 degrees, so really substantially different. What we find is that for SSP 126, we project that the glaciers will lose about 27% of their mass over the next 85 years, all the way out to 2100. And then for that higher emission scenario, we're looking at the glaciers losing about 44% of their mass. Part of the key findings that we had, and this was published as a cover article in Science last year, is that the glacier projections that we estimate we estimate about 10% more mass loss than previous glacier projections that were used to inform the IPCC assessment report. And so really the planning that goes into sea level rise, for example, relies heavily on that IPCC assessment report figures. And so it's actually underestimating the contributions from the glaciers. So really important. Now, another key aspect of what we do is we really translate these emission scenarios into policy relevant temperature change scenarios. I've been fortunate to go to the Conference of Parties. I actually just got back from there last week. I went the year before as well, and be able to share this with policymakers to try to support bringing science into the decisions and the climate pledges that they're making. And so here, what you're seeing on the left is the percent mass remaining from 2015 to 2100 for those different temperature increase scenarios. And you can see at the end of the century, for a 1.5 degree increase, we're looking at losing approximately 25% of the glaciers. For a +4 degree scenario, we're looking at losing about 40% of the glaciers. And what's really important to recognize here is that current climate pledges, they put us at about +2.7 degrees increase. So we're losing somewhere in the middle of those. And now the figure on the right is showing you really a clear linear relationship. You can fit a line through those points quite clearly. And that's the mass that's remaining at the end of the century. And so what that means is that every increase in temperature really matters. In other words, our actions as a global society in reducing our greenhouse gas emissions really controls what's going to happen to these glaciers. Now, as I showed before, right, we now have measurements of every single glacier that we use to calibrate our model. And so we can really get into the glacier areas, subregions, to think about how are these glacier changes in the future varying across the world. And so here the map is showing where you have blue colors, you have about 80% of that glaciarized area remaining at the end of the century relative to 2015. The redder colors are showing you where you have less than 20% of the glaciers remaining. And then we also really highlight areas that are becoming completely deglaciated. And so these are the white circles that are outlined in black. And now this map is showing you a 1.5 degree scenario. As I click through, you're going to see 2 degrees, 3 degrees, 4 degrees. So you see that we're getting more mass loss, a lot more red, and a lot more deglaciation all around the world. In fact, for areas like Central Europe and a lot of the mid-latitude regions, they still have ice remaining at 1.5 and 2 degrees, albeit a lot less than present. But when you look at those higher temperature change scenarios of 3 and 4 degrees, you're almost completely deglaciating those regions, losing all of their glaciers, which would really be a catastrophic change. Now, as I mentioned, one of the most important impacts of why we study these glaciers is sea level rise. So here I'm showing the glacier's contribution to global mean sea level rise from 2050 to 2100 for those different temperature change scenarios. We see that if we can keep our emission scenarios in the future and really improve our climate pledges to meet that 2 degree Paris Agreement level and try to take action to get it down to 1.5 degrees, we're looking at less than 100 millimeters of sea level equivalent. So the glacier is contributing about 3.5 inches over the next 85 years. If we don't take action, or if we have those higher temperature change scenarios, we're looking at upwards of 130 to 150 millimeters, or roughly 6 inches. And a key thing to remember is that the glaciers are just 20% of the global contributors to that global mean sea level rise. So the actual sea level rise estimates are considerably higher than this. Now, I want to take a step back and think about the broader context of these glacier projections because they are just one contributor. And when we think about the impacts associated with sea level rise, it's really important that for communities all along the coast, what they really care about is really localized relative sea level rise. And what this includes is how is the land changing? So things like subsidence can be really important, as well as regional variations. So as we lose ice from the glaciers and the ice sheets, it actually changes the way that weight is distributed on our planet. And that causes more sea level rise in some areas and less in others. So that can be really important for regional sea level rise as well. The other thing to recognize is that communities typically experience the extremes of sea level rise. They're less really concerned about just the general mean sea level rise, but more is how is that mean sea level rise going to amplify already extreme rates of sea level rise. So things like storm surges, waves, high tide, nuisance flooding on top of sea level rise is what they're interested in. In fact, sometimes you go even further and they're interested in compound events where you start to think about sea level rise, as well as that extreme sea level of a storm surge or a high tide, as well as an extreme precipitation event all happening at the same time. And the impacts associated with this really vary by region and community. It can include things like the permanent loss of land, permanent loss of infrastructure, more frequent, more intense flooding, coastal erosion, the salinization of our soils and our water resources, our groundwater systems, loss of ecosystems, as well as impeded drainage, which can be problematic for stormwater in cities as well. So what can communities do? There's lots of different adaptation strategies. They can protect their infrastructure. This is typically by doing things like building a seawall, for example. They can accommodate, doing things like elevating their homes or planting salt-tolerant crops. They can advance, which is really building new land, trying to protect and raise the elevation at the same time. They can retreat, which is often thought of as a worst-case scenario where people are going to move out of those hazard areas. And then ecosystem or nature-based solutions are becoming very popular at the moment for good reason, in that they have both the effects of protecting as well as advancing, because things like wetlands can actually accumulate sediments as well. Now, one of our current research projects that's funded by the National Academies is really looking at how can we help communities in the Gulf become more climate resilient, and specifically using a newer adaptation strategy called dynamic adaptive pathways. And what this is the term dynamic refers to communities being able to develop adaptation strategies for a range of future scenarios that build on one another. And this is thought to be a cost-effective strategy because the communities can invest in strategies to reduce the impacts associated with current or near future sea level rise. And then they can implement additional adaptation strategies in the future, depending on how bad things get, right? So if we reduce our greenhouse gas emissions, if we're able to mitigate a lot of that sea level rise, maybe you don't need as much adaptation as if we went on with business as usual. Now, part of this project, it's really focused on connecting to communities and decision makers. And so we do focus groups, and we found that they really like the idea of this dynamic adaptive pathway tool, but they didn't have the resources or the knowledge to actually evaluate how effective different adaptation strategies would be. And so fortunately, we were able to really transform the scope of our project. And what we ended up doing was start developing these compound flood models and pairing them with damage models using this tool called Flood Adapt that Deltares has developed. And so this allows us also to look at how different adaptation strategies, how effective they're going to be in reducing flooding and reducing those impacts. So here I'm just going to show an example for South Carolina. Let's say a theoretical, we put a 12-foot seawall around the coast. So here's what flooding would look like for a 50-year rainfall event with present-day high tide conditions. Here's what happens if you add a foot of sea level rise. So you can see we get a little bit more flood depth as well as a little bit more area that's flooding. Here's what happens if you add a 12-foot seawall, right? So the nice thing is that this tool, it allows a user or decision maker to be able to look at various adaptation strategies. We can look at various rates of sea level rise. We can look at all sorts of things and see what is the flooding there. We can also get feedback on our models. They can look at, oh, well, this flooding for this event, it didn't flood there, or it flooded over here. And so we can actually go in and improve our models as well, which is exciting. And the other thing that we can do is we can start to look at the socioeconomic impacts. So as I mentioned, we have this damage model. It's connected to census data. And one of the things that we're really trying to do is think about how can we center equity within these adaptation strategies frameworks. Now, as I mentioned, sea level rise, it often receives a lot of attention, but these glaciers are also really the world's water towers. And I love this figure. The glaciers are important for areas of South America and Europe as well. But it's really striking that more people live inside of that circle than outside of it. So in high mountain Asia, they're really an important water resource. When we think about how glaciers are going to look in the future, think of the glaciers as being just a natural reservoir. And as you start to melt the glaciers, you're essentially releasing water from that reservoir. So there's going to be a time where you actually get more water downstream. But over time, you start to deplete your reservoir and you just simply can't produce or provide as much flow downstream. And so you get this peak, but then after you've depleted your reservoir, you start to see a decrease. And that peak we refer to as peak water, both for the timing and the magnitude of it. So in high mountain Asia, I'm going to show examples of two different basins. We can look at how the peak water varies for those different emission scenarios, those SSP scenarios. And in the Indus, for example, where there's a ton of people living downstream who rely on this water, we see that we expect peak water to occur sometime around the middle of the century. And it occurs later for those higher emission scenarios because we're simply melting more and more of the glaciers. So this is good news for the Indus in a way, because a lot of the Indus relies heavily on groundwater. And so if you have more glacier water, you don't need to worry about, or you don't need to rely on your unsustainable groundwater as much. Now in the Brahmaputra, on the other hand, again, highly populated area, we estimate that they've already passed peak water, and then in the future, they're going to have roughly 20 to 30% less glacier runoff moving forward. And so that means that they're going to stress an already stressed groundwater system. Now, the complete story really requires a hydrological model. We're taking our glacier runoff, and we can do this. We take our glacier runoff, we put it into the hydrological model with our colleagues from the University of New Hampshire. We track it as it moves down the system. We can look at this in various river basins. And we can even look at how is that glacier runoff being used in irrigation, for example, and how is that going to change over time. Now, the last thing I want to give you a little teaser of is I mentioned that these are very important for socioeconomic activities. This is a picture of Marjorie Glacier, which receives about 500,000 visitors a year because this is right on the cruise ships. If you've ever gone on a cruise in southeastern Alaska, it's very likely that you went and visited Marjorie Glacier. Now, we can look at the projections of Marjorie Glacier. This is a cross-section. The different colors are showing you those different temperature change scenarios. And essentially, you can see that the glacier, roughly around the middle of the century, retreats from terminating to ocean to retreating onto land. So this tidewater glacier, you're not going to be able to see it as well in the future. But there's a big difference between 1.5 degrees where it's really still far down near that ice-ocean interface compared to higher temperature change scenarios where it's retreating much higher. Beyond economic activities, these glaciers can be very important for local cultures. I'm going to close with a story of a glacier in New Zealand. Its Maori name is Ka Ruimato Hinehukatere. Its name literally means in Maori, the tears of the avalanche maiden. And it's based on a Maori legend that describes how Hinehukatere, she took her lover Tuave up into the mountains. But Tuave couldn't keep up with her, and he fell, and an avalanche swept him to his death. And Hinehukatere, she cried, and she cried, and she cried, and her grief was so pronounced, and her tears were so excessive, that the gods froze them as a perpetual memorial to her sorrow and to her regret. So here you can see photographs of how this glacier has changed over the last 150 years. And as a Maori individual eloquently put it, it's more than just a physical loss. It's a spiritual depletion, a depletion of our ancestral heritage, and a devaluation of our past. So the glacier is still here today. It's just significantly retreated. Our projections show that the glacier could lose only as little as 20% of its ice, while for those higher temperature change scenarios, it could lose roughly 85% and retreat to much, much higher elevations. So I'd like to leave you with one closing thought, and that's really that these glaciers tell us stories. Quite literally, they're embedded within our oral traditions of those who have lived by these glaciers for centuries, but they also tell us a story of change. At national parks, World Heritage Sites, mountain ranges all around the world, they sometimes share with us their beauty and their majesty. In other settings, they share stories of loss. They share stories of their impacts. They share with us a clear story of climate change, and their loss really reveals the considerable impacts to sea level rise, water resources, cultures, economies, spiritual traditions all around the world. And so what our work is really doing is it's seeking to focus on both the climate mitigation piece while also recognizing that we need to think about adaptation and we need to support communities and becoming climate resilient in the future. So with that in mind, it's really important to remember that every increase in temperature matters. That means that we as a society, we have the ability to make a difference. We can write what the story of these glaciers looks like in the future. Thank you very much.
Okay. Thank you, David. We really appreciate all these great insights that you've shared with us today. And what a poetic ending to your research. So thank you.
Thanks.
We will now turn to our audience for questions. As a reminder, please submit your questions via the Q&A feature at the bottom of your screen. Make sure you include your name with your question. And I think I'll start here because you mentioned you recently presented your work to international policymakers. Can you share a little bit more about who you spoke with and how your research has actually supported their work as well?
Yeah, so the last 2 years I've gone to the Conference of Parties. 2 years ago it was in Dubai, this year it was in Baku. And that's really where all the countries are coming together to try to come to some consensus as to emission pledges. How much are they going to reduce their emissions? Really trying to stay in line with the Paris Agreement that they agreed to many, many years ago of keeping that temperature increase to 2 degrees. Now, there's also loss and damages funds and all sorts of other activities that go on. My primary responsibility there as a scientist is to try to equip the policymakers with as much information and really lead their decisions by the science. So in years past, last year, I spoke with the president of Switzerland, foreign minister of Chile, and really trying to get them to think about when they're going into these negotiations, why it's so important to think about the cryosphere, how much loss is already baked into the system, how much these impacts are both in their regions, but also globally, and really try to enable them to have little sound bites that they can use in that negotiations to try to help spur some more climate pledges, really.
Well, thank you for representing CMU so well internationally.
Thanks.
I've got a question here from someone from the class of 2022. And he asks, are there any limitations to the satellite technology that we're using to gather this data?
Yeah, that's a great question. So we're actually involved in some new missions associated with NASA that's really trying to push what we can do with respect to observations. So really, as we start to think about pushing the boundaries of satellites moving forward, we also need really detailed in situ measurements in order to be able to validate what those satellites are actually seeing. There's been tremendous development in really different types of satellites, optical satellites, synthetic aperture radar satellites, stereo imagery satellites, where you can recreate elevations. Most of those have very little limitations. So for example, stereo images, we now get to the point that as researchers, they give us a resolution such that you can identify people, right? So we have really, really high resolutions. It's really developing the tools that are able to utilize and leverage those data.
Fantastic.
Great question.
We have another question from someone here named Mark, and he's asking, do current models show climate change slowing in the future?
Yeah, that's a great question. So we do, I showed projections only going out to 2100. For most of those, you can start to see in some regions that at the end of 2100, for those 1.5 degree temperature change scenarios, the mass will actually start to level out. If you go beyond to 2300, you can actually see the glaciers start to gain a little bit of mass. Now, I'll note that the way that glaciers respond to changes, it's a lot easier to melt glaciers than it is to regrow them. So we might lose glaciers over a 50 or 80-year period, but regrowing them can often take centuries, significantly longer. And that regrowth, it only gets us like 10% more or 20% more than in 2100. So we're still losing glaciers as a whole, but it at least is stabilizing the glaciers and putting them in a happier state, which is important.
So going back to the kind of the climate talk internationally, what can we do here? What policies can we pay attention to as voters?
Yeah, I mean, the most important thing is really being informed and trying to bring that knowledge to your local representatives or nationally. What I found with COP29 is really that people are really trying to move forward regardless of what happens if the US pulls out of the Paris Agreement, for example. So people are really trying to lead. They recognize how important climate change is and all of the impacts associated with it. And so for us, whether that's at the state level, the local level, really the ways that we can reduce our greenhouse gas emissions, the ways that we can start to transform our societies in that way can really help mitigate a lot of these impacts. We're going to lose glaciers regardless. So we're going to have some amount of impacts that we have to adapt to. It's just the extent that we can adapt is really going to be driven by how much we're able to reduce our greenhouse gas emissions.
So thank you, and thank you for sharing this with us so we can be informed voters. I actually have a question here from someone from electrical engineering class of 1957.
Awesome.
And they have asked, are there any glaciers left in Glacier National Park? And if so, when would they disappear?
Yeah, so there are glaciers that still remain. They're a specific type of glacier called a cirque glacier, which is essentially, if you've ever been to Glacier National Park, I suspect you have, asking the question, but they're essentially in these really small basins that are really guarded. It's a little mountain cirque. And so it's a small glaciated area. Most of them are stopping flowing, or they're not really flowing that much, which is really one of the key characteristics that we have of calling a glacier, is that it flows under its own weight, and they are being lost. So I'd have to go into the specific projections. We do see that we expect those to be deglaciated at some point in time we see them in the 2100 maps, but I don't know the exact year that our model would estimate those, unfortunately.
Thank you. And hopefully I can pronounce this correctly. We have a question from Ned, and they're asking, do your models include changes in the solar insolation from the Milankovitch cycles and similar long-term cycles, or is the temperature the independent variable for your models? Ned must know something here.
Yeah, it's a great question. So yes, so our glacier model is using temperature and precipitation estimates that are coming from the general circulation models. And so those general circulation models are using things like, the rotation of the world and how it's moving around the planet and those types of things. So it's factoring in what the future of Earth looks like. Sometimes you're starting to see these general circulation models, or sometimes you hear them referred to as global climate models. They're increasingly being referred to as Earth system models because they're essentially coupling all the elements of the Earth's land with the climate model and ocean models as well. So we specifically aren't including those processes in our model itself, but the forcing data that we use does. Good question.
Great, thank you. So something a little more recent here. Both hurricanes Helene and Milton led to considerable damages in the southeastern United States. How does your work on sea level rise and adaptation strategies fit into extreme events like these?
Yeah, it's a fantastic question. So I'm going to give a little bit of a nuanced answer here. So on the one hand, a lot of people who we talk to, it's very hard to adapt to a scenario like that large of a hurricane, right? Like we literally, it requires really massive adaptation strategies in order to do so. And really only mega cities could be able to put things in place like that. And you see the impacts in, Hurricane Sandy, like you name it, Katrina, mega cities even will experience some impacts. So when we talk with communities, it's really trying to support their adaptation to a little bit smaller events. So compound flooding events, and we're talking about 50-year, 100-year storms, but not necessarily, a hurricane, a category hurricane that is going barreling right up directly on top of that area. We do typically include some smaller storms, so like category 1s, 2s, and 3s. When we're doing our modeling and our validation, part of that is because there's actually a decent amount of data after hurricanes as to like the flood extents and the damages that we can use to assess our models. It's also helpful to contextualize our model with community members in that relation. But the other thing so there's a little bit of adaptation planning that goes involved to those types of events on the slightly smaller scale. But the other thing is it's thinking about after these events occur is often when there's a lot of stimulus that comes into these communities in order to build them back. And so you have the ability at that time to either build back the same or to try to build back a more climate resilient community. And I think that's really the key here is once you have those events and after you have some funds coming in that can really support this adaptation, to make sure that we're doing that in a way that's going to make that community more climate resilient moving forward. It's a great question.
So a little personal to you, you have a beautiful photo behind you. I picked mine from Google, but I have a sense that yours might have been taken from your own camera. Can you tell us about your own experiences on glaciers and maybe what's happening behind you there?
Sure. Yeah. So this was from last April. We were out on a glacier, Galcana Glacier in Alaska. This is where we've been conducting fieldwork for the last 3 years with USGS. Every now and again, you get the skies to completely open up and the auroras start to come. And, we typically are working 12 to 14-hour days while we're out in the field because it's pretty light in Alaska in April and August. But sometimes you just have to take your sleeping bag outside and just really soak in the beauty of the area that you're in. But yeah, we do a lot of glacier field work in order to, as I mentioned, to really push our models forward. We can get a lot better detailed understanding of the processes that we can then scale up through modeling. Also to take more advanced measurements that we can then compare and evaluate different remote sensing products. And so this is our one glacier area. In June, we'll go to Ecuador. We have some work on tropical glaciers in Ecuador, really high elevations up there. That's how they survived. And then it looks like we have a project coming in to do some field work around Juneau on ice dam glacier lake outburst flood. So one of the benefits of the job is that we get to go and experience these. At the same time, it's pretty cold. So we got our -40 sleeping bags and we try to stay warm.
Do you have the opportunity to take any of your PhD students with you?
Yes, I always take PhD students. They're each of these projects. So for the last 3 years, I've taken 2 of my PhD students and have 2 more PhD students coming on for the Ecuador and the potential Juneau project. So.
And see, I did my summer internship at Cedar Point in Ohio. So these students are certainly getting an experience of a lifetime.
It's a wonderful lab.
Yeah, absolutely. I'd like to ask the audience if you have any more questions. Otherwise, I'm going to start asking David about penguins. So if there's any more questions, you can add them to the Q&A. No? Well, was there anything else, David, you'd like to add for the good of the order here?
I think I shared everything that I hope to. It's easy to, I get asked a lot, how do you study glaciers? Isn't it depressing to see how much they're losing? And I think it's easy to have that feeling of climate anxiety can be very real. At the same time, what we show a lot of is really that like our actions can have a big impact. And so I try to lead with a message of hope that we can really make a difference. So I hope everybody leaves this feeling a little hopeful at least.
Well, you've certainly made me feel a little better, and I really appreciate you taking your time, and I wish you and everyone on the call today a very happy Thanksgiving or holiday weekend.
Thank you so much.
All right, thank you.